Let's imagine this scenario. Is a transmission necessary for electric trains in the first place? As introduced in the torque video, in diesel engines where the rotational force is almost constant regardless of the speed, the usable output is proportional to the speed. Even if the rated power is 500 horsepower, if the speed is half of the rated speed, the output is also halved. The transmission compensates for this, allowing the engine to work effectively regardless of the train's speed. On the other hand, electric trains primarily use DC series wound motors in the past, and now AC motors such as induction motors and synchronous motors. For DC motors, if the speed drops, the rotational force becomes stronger, almost inversely proportional to the speed. On the other hand, this is not the case with AC motors. However, AC motors can freely change rotational force and speed depending on the settings of the control device that changes frequency and voltage. Nevertheless, to obtain strong rotational force, a large current is required, and from the perspective of heating, there are limits to what the control device and motor can withstand. In the era when the DMH-17 was mainstream in diesel multiple units, DMUs, almost all vehicles, from express to local trains, ran with the same reduction ratio. The 80 series DMU express trains were slightly different, but the difference was minimal. On the other hand, EMUs were classified into 4 categories: limited express, express, suburban, and commuter, each with different reduction ratios depending on whether low-speed high acceleration or high-speed running was prioritized. This fixed the usage, making it impossible to reuse available vehicles. In the mid-Showa period, when new performance EMUs were successively introduced and mass-produced, effective utilization through vehicle reuse became a challenge due to economic growth and urban concentration. The EMUs with commuter and suburban performance, which were heavily deployed for commuter transportation in metropolitan areas, were idle outside rush hours. On holidays, their usage significantly decreased. On the other hand, during the travel boom that reached the general public, there was a shortage of vehicles for medium and long-distance transportation on holidays, and deploying vehicles solely for that purpose was economically disadvantageous. Thus, the gear-changing bogie was proposed. Although it couldn't switch gears while running and couldn't be called a transmission, it incorporated a mechanism to switch between low-speed and high-speed modes. Similar to the auxiliary transmission in off-road vehicles, it was akin to the mechanism found in railway vehicles like the DE-10. During the commuter rush, it was set to low-speed mode for commuter use, and on holidays, it was set to high-speed mode for express use. The structure placed the motor in the center of the bogie, connected to the gear-switching mechanism, with the output transmitted to each axle. While the mechanism itself worked well, converting commuter vehicles to express use was impractical in terms of passenger amenities. Although prototypes of long seat and cross seat conversion mechanisms were made, issues such as low backrests prevented practical use. Would this mechanism have been effective if it had developed and been utilized as a transmission? Precise electronic control technology was not available at the time, so shifting gears while running might have been difficult. However, as shown in the video on mechanically controlled induction motor trains, an 8-speed transmission mechanism was realized. So it might have been possible with electric motors of just a few hundred horsepower. Moreover, since this was a DC series wound motor, a complex 8-speed mechanism was unnecessary, and a 2-speed mechanism would have sufficed. What if limited express EMUs had a reduction ratio similar to suburban EMUs? Considering the 1960s, one thinks of the problem the 151 series limited express EMUs faced with the Sino-Hachi incline. The 82 series DMU express trains with transmissions climbed the Sino-Hachi slope without difficulty, albeit slowly. The 151 series, which had to rely on helper engines, might not have had this problem if it had this mechanism. As a low-speed mode, let's give it the reduction ratio of 4.82, which was the reduction ratio for suburban EMUs at the time. In low-speed mode, acceleration performance in the constant current region after departure naturally improves, but it enters the weak field region at 49 km per hour and must switch to high-speed mode before reaching 70 km per hour. In parallel full field operation at the third notch, it slightly falls below 60 km per hour at a 25 per mil gradient, but this allows it to run at nearly rated current. At Sino-Hachi, Considering the curve resistance, it equates to a 25 per mil resistance, and with a curve radius limit of 300 meters, this speed is generally permissible. With the original reduction ratio, the current decreases to rated current at speeds exceeding the speed limit, but with a transmission, it stays within the allowable range. With a transmission, the initial acceleration performance would be equivalent to suburban EMUs, but would it have affected travel time for limited express trains with few stops? Comparing the number of stops of the Tsubeim at that time between Shinosaka and Hiroshima, the acceleration is good right after departure with the suburban EMU reduction ratio in low-speed mode. However, there are no other situations to utilize this performance, resulting in only a 61-second difference to Hiroshima. When calculating the standard running time in 15-second increments, there is still only a 1-minute difference. Ultimately, even with a transmission, there is no noticeable effect outside of Sino-Hachi, and with the spread of 120 kilowatts motor-equipped cars, helper engines were abolished. There is no point in creating a transmission bogie by adding complex mechanical mechanisms. On the other hand, there were still difficult sections where even 120 kilowatts motors were insufficient. At Yuzhui Pass, even after switching from the ABT system to adhesion operation, all trains still required helper engines. Self-powered climbing was being considered here. With 120 kilowatts motor-equipped cars, it might be manageable with the reduction ratio of suburban EMUs. How about a 115 series EMU with a 6M2T formation? It seems it could climb, but it would significantly exceed the rated capacity, and naturally, the resistors and motors would burn out. What about an all-M formation? This would stay within the rated capacity, making self-powered climbing of Yuzhui Pass possible. If climbing is the only consideration, no special new development elements are needed. However, it would be difficult to operate a limited express train with the reduction ratio of a suburban train, leading to the introduction of bogies with transmissions. Since the low-speed mode is only needed for climbing Yuzhui Pass, the previously mentioned gear-changing bogie would suffice. What if the 181 series EMU with an 8M4T formation had the reduction ratio of a suburban train? With 4 trailer cars in the formation, it cannot climb with the suburban reduction ratio. Therefore, let's assign an even higher reduction ratio of 6.07, which is the reduction ratio for commuter trains. This provides more than 20 kg/ton of acceleration margin against a 66.7 per mil gradient, making it possible to climb. Even at rated capacity, the performance is only slightly insufficient, and as long as it doesn't stop midway, it can climb in the third notch. In practice, intermediate stops must be considered, and in such cases, it takes about 3 minutes to accelerate to near the rated speed of the full-field final stage. To allow for more margin, it seems necessary to reduce the number of trailer cars. Later, serious consideration was given to self-powered climbing of Yuzhui Pass by EMUs, and surplus SARO 183 cars were modified, planning lightweight vehicles with a lower reduction ratio. The configuration was planned as an 8M1T formation, and although the design progressed, it was never realized, and with the opening of the Shinkansen, the pass itself was abandoned. The Battle of the Pass, challenged with various innovations, came to an end. How about the Shinkansen? The 0 series EMUs were equipped with 185 kilowatts motors, which were considered high output at the time. However, the reduction ratio was low at 2.17, designed for 200 km per hour high-speed operation. With a rated current of 490 amps and a current limit of 570 amps, the average current during acceleration was about 620 amps. As the speed increased, the voltage difference between the transformer taps decreased, gradually reducing the average current, but it did not significantly decrease until around 150 km per hour. The overcurrent ratio was just over 20%, and combined with the heavy body, the acceleration was quite poor. Compared to the 151 series Kodama with a 6M6T formation, the 0 series lagged behind in initial acceleration. What if a transmission was added and the low-speed reduction ratio was increased to 3.0? As shown in this figure, the initial acceleration would improve significantly, surpassing the 151 series Kodama, and this acceleration would continue beyond 100 km per hour. How would this performance affect travel time? Without ATC, and only considering speed restrictions due to curves and turnouts, the running curve would look like this, resulting in a reduction of just over 20 seconds per station. Even for all station stops like Kodama, the reduction effect is only a few percent, and for Hikari, it's about 1 minute. Developing a complex device for this is not worthwhile. Moreover, with the rapid advancement of power electronics technology, induction motors without commutators, capable of handling high currents and high-speed rotation, have been put into practical use. High-output motors can now be housed in bogies, allowing Shinkansen to handle startup currents well above the rated capacity. At this point, there is no need for transmissions in trains like the Shinkansen. With the high performance of motors, the era has come where no new drive systems are needed in railways other than direct drive, where the axle and motor shaft are the same. On the other hand, with high performance, motors are entering new fields, and aircraft and automobiles have different requirements from railways. Aircraft require lightweight motors comparable to gas turbines, leading to research on various ultra-lightweight motors to address the heavy iron and copper components. In automobiles with high adhesion performance, there is an expectation for transmissions to handle rough terrain, making them indispensable for tanks and heavy machinery. The use of motors in different industries may influence railways in the future.